So we know that we only have a small number of stable nuclides, right? That those combinations of protons and neutrons that are stable, and everything else would be unstable. And so what that means is that that nucleus will fall apart. There is something about it that is unstable. Because nuclei are trapped in the middle of an atom, they can't really interact with each other. So the only real option available to a nucleus is to fall apart, and that's where we call it decay. So the nucleus is unstable, the balance of it's too big, the ratio, whatever it is, of protons and neutrons doesn't work. And so as a result, it's just going to fall apart. So this doesn't always, when we say that nucleus is unstable, that doesn't necessarily mean that it falls apart instantly. Different nuclei have different relative instabilities, right? We said that nothing above 83 was stable, but there are certainly elements that we know about up there. Uranium, for example, uranium-235 is a pretty relatively stable isotope that's up that high. It still is unstable, but it takes tens of thousands of years to decay. So, those nuclei that exist are generally going to be sticking around. Something like californium-238 takes tens of milliseconds to decay. So that is very unstable, and that nucleus really has a tendency to just fall apart. So the thing is, these decay processes where you have nuclei falling apart there's a huge amount of energy that is associated with those. These processes, in order to happen, are spontaneous, right? And there's not really much changes in the entropy on this side of things. It's all in the enthalpy. The reason why nuclei fall apart is that they are relatively unstable, and they change into a new nucleus with a new composition of protons and neutrons that is more stable. It has a lower energy. And so there's an associated release of radiation, right? And radiation just means energy that is sent out from the nucleus. Energy leaves the nucleus, right? That nucleus was unstable. It basically just spits out that energy, and then the nucleus becomes more stable at a lower overall energy. And any nucleus that is potentially going to decay and emit radiation, we call a radioisotope. So when we talk about this graph that's here, shows those same combinations of protons and neutrons, and the black dots are all of the dots that we said were the stable nuclei. Well, you can have all sorts of other nuclei, right? You can add some extra protons or add some extra neutrons, different directions, and you'll see all those different colors correspond to the very large number of possible nuclei that are going to be unstable. And again, just because it's unstable doesn't mean it falls apart instantly. But that there is some time. So that's how we can characterize these things. It may take years, hundreds of years, thousands of years, millions of years to fall apart. But the universe is a little bit older than that, and so it takes anything that we would have would fall apart or go away. So when we start to talk about these decay processes, we're going to talk about protons and neutrons that are in the nucleus that are going to be changing in different ways. We're going to treat them as just, we've shown pictures so far. They're just little spheres kind of hanging out, clumped together in a nucleus. It's important to note that this is a simplification. Protons and neutrons are really small. Hence, you need to use quantum mechanics to actually describe what they're doing, in much the same way that we need to use quantum mechanics to describe electrons. There's that wave nature, particle nature to the particles that are inside a nucleus. So they're not just little spheres all clumped together. We still are going to talk about them as if they are. And the reason is it's not necessarily worth it to develop this really overly complicated description of using the quantum mechanics of the protons, neutrons, and nucleus wave functions when we can just instead get the same gist of the idea just by talking about them as particles. Much the same way electrons really have, these orbitals. They're very complicated things, but we still kind of talk about them in a lot of ways as if they're like planets orbiting a nucleus. And so the reason that we can use this, that model is useful, right? And so we're going to talk about these things. There is another layer of complexity. Certain things we're going to talk about are going to seem kind of nutty. How do those happen? And it's all in the very complicated world of kind of the quantum mechanical description of what's going on in these nuclei. So keep that in mind. I don't expect you to look into that or understand that. We're going to touch on it a little bit here and there. But for the most part, we can just think about these protons and neutrons as little spheres. They're going to change. It's not real. There is another level of complexity, but we're not going to worry about it. All right. So when we're going to start to talk about these ideas of decay, there's going to be things that are going to get kind of spit out from the nucleus, right? Different, not only energy, but particles. And so when we talk about these particles, we're going to use the same notation that we have used to talk about nuclei. So the top, we can say we have like a proton, a neutron, and an electron. Those are the particles that go into atoms. And we can describe them if they are outside of an atom. We're going to use a symbol, the letter, which is going to mean the first, it's just the first letter of that. So P is for proton, N for neutron, E for electron. And then the top number is the mass, and that bottom number is the charge, excuse me, just like we had for nuclei, right? It was number of protons, which was charge on the bottom, and then number of protons plus neutrons. One of the things you'll note is that electrons do technically have a charge, but we've written the charge up there as a 0. The reason for that is that in the context of nuclei, we're counting the number of protons plus the number of neutrons, right? And electrons don't have either of those, so they technically, in this case, would have a mass number or an atomic mass of 0 because they're just an electron. So there are a lot of types of radiation associated, or types of particles and types of radiation associated with this decay. We're going to walk through these one at a time as we go through this, but this is just a chart that's showing the names of the particle, the associated type of radiation, the symbol that we're going to use, then the particles, again, just like nuclei, what we care about in terms of properties is charge and mass. So there's all these different kind of things that can come out of a nucleus, be involved in radiation, and they'll have charges and masses. We've seen, protons, electrons, and neutrons. That's kind of the stuff the particles we've already talked about. Some of them have fancy names in this context, but there's also going to be some new ones that we're going to talk about that have associated symbols and that sort of a day. But we'll walk through these one at a time, but here's a reference we can always come back to with all the properties of all of our radiation. All right, so when it comes to different types of decay, there are 5 types of decay that we're going to talk about. For the purpose of making the videos a little shorter, I've broken them up into 2 groups. And this one, we're going to talk about what is kind of called the traditional decay. It has names like alpha, beta, and gamma. These aren't, when I say traditional, that corresponds to historically how humans figured them out. There are 3 types of radiation that make it out of nuclei that were unique. We thought they only could come from nuclei, and we didn't know what they were. And so people didn't know what they were, but they knew there were 3 types. So they called them alpha, beta, gamma, which is A, B, and C with the Greek alphabet. And so you can go through that idea right there. Positron emission and electron capture are more complicated to figure out, so they were more recently. By the time we figured out what those mechanisms were, we also just knew what the particles were. So those names are more explicit. So we'll get to those in a second video, but it's all the same idea where it's all about you take a nucleus and that is unstable and it's going to undergo some process to become stable. So the first type of process is called alpha decay. And in alpha decay, an alpha particle is emitted from a nucleus. So you have some sort of unstable nucleus, and that unstable nucleus loses an alpha particle. So we talk about radiation, that alpha particle comes out and is now shooting away from the nucleus. So what an alpha particle is, it's just a helium nucleus, a helium-4 nucleus at that. So a particle is emitted from your nucleus that is 2 protons and 2 neutrons. And so in terms of notation, historically, we call it is an alpha particle is the name. But a lot of times, and I will just use, because we're chemists, we just call that helium, right? It has a name. It is a helium nucleus. And so I'll oftentimes just use the helium symbol, helium chemical symbol, but you'll still see alpha little letters. So just kind of, there's then an equation. So these are chemical processes, right? You have atoms that are changing. And so we can describe that. And so, you'd start with your reactant, which in the case of most decay processes is just going to be one nucleus, which we call the parent nuclide. Okay, so parent then leads to the creation of a daughter nuclide, and then you emit the radiation particle. Okay, so you start with one parent nuclide, some sort of radiation, in this case a particle is emitted, and you make a daughter nuclide. So in terms of this actual process for alpha decay, if you had a uranium-238 nucleus, you start with a single particle, a single nucleus, that undergoes a decay event where it just spontaneously falls apart. And then you spit out the alpha particle and the daughter nuclide is left over, or the daughter nucleus. And so that is left over. Because there's a different number of protons in that nucleus, it has a new name, right? You started with a uranium nucleus, it has now become a thorium nucleus because it has a different number of particles. The electrons around that nucleus will adjust, right? You now have functionally a different unequal number of protons and electrons. The electrons will adjust, and this atom will now gain the properties of thorium. So a different atom type, that's a different element that will have different properties itself. This alpha decay, alpha emission is most common among heavy nuclei. So something like uranium, it's pretty big. Those sorts of big, the bottom of the periodic table is where you start to see a lot of alpha emission. Okay. So when we start to look at nuclear reactions and nuclear processes, one of the things is we can actually predict what sort of daughter nuclide we're going to make for a given type of decay. And it's based around the idea that you need to conserve two things. Well, really what you need to conserve is the particles, right? If you started with, protons and whatever the mass of all your protons and neutrons, you need to end up with that mass for all your protons and neutrons. Whatever charge you ended up with, in this case, the total number of protons, you need to have that same total charge. So the mass, again, is the numbers at the top of the symbols. So in this case, you started with 238 total nucleons, that's protons plus neutrons. In your products, you need to have that same total number of protons and neutrons. It's split between two particles, 234 and 4, between the two particles, but it still has to add up to 238. Similarly, with the charge, all the numbers at the bottom, he started with 92 total protons. That was plus 92 charge. You now have across two particles, the plus 90 in the thorium and the plus 2 in the helium. So with this idea of balancing, we want to take it and we then want to be able to figure out something like what is the daughter nuclide formed when radon-222 decays via alpha emission. Okay? So we know we want to be able to predict, we're starting with radon-222, it's going to undergo a change, it's going to go alpha emission, what is going to come out from that, right? This is the same question we've asked, similar, if you do an acid-base reaction, what are the products? Right? If you mix two half reactions in your electrochemical cell, what's the chemistry that happens? What products do you make? If you do electrolysis, you push it, what products can you get? This is the same idea. We're going to be able to predict these changes. They're not necessarily chemical changes, but we're going to make new atoms. What new atoms are we going to have? And so the question when we're working through this is always going to be, what is our starting nucleus? That's going to be, there's always going to be some information given. You need to have information on either starting nucleus or potentially daughter. You're either your parent or daughter, but you need something. In this case, that's going to be, we can see radon-222. One thing I also want to note, we're going to be dealing with a lot of the periodic table. Remember, you can always look up information about radon. So you're told the mass number is 222. You're going to also want to know the atomic number. Don't expect you to memorize that. Look it up for what radon is. Especially, we're going to be dealing with a lot of elements you've probably never dealt with before. And so, I have no idea what radon's atomic number is. Don't feel like always use the periodic table to look these information up. And so then we know that's the starting nucleus. We're always also going to be given information about what type of decay process is going on. So in this case, we can see it's alpha emission. We're not necessarily told what it is, but that means it's going to be an alpha particle, which we can either look up or know that that's a helium nucleus. And then we can use balancing. We can know that the charge has to balance and the mass has to balance. We can figure out what has to be left over if an alpha particle was emitted. All right, so we start with radon-222. If we look it up, radon has an atomic number of 86. So that's how I figured out the 86 there on the bottom. 222, that information is given because you have to know what particular radon isotope, which radon isotope it is. But you're given the fact that it is radon 86 as the same thing as calling it radon, 86 protons. Okay, so we know it's alpha emission, which means we're going to emit a helium-4 nucleus. So that means we would draw our arrow to denote products, and then our helium-4. This is always, when we say alpha emission, we're always talking about emitting a helium-4 nucleus. So then, once we know that, there's always going to be three components, right? You have the parent, you have the particle, and then you're going to have the daughter. And so we just, in order to figure out what that daughter is, we're going to balance the mass to start off with. We know we started with 222 as our total mass. On the product side, we have 4 mass in the helium. Then the other nucleus has to have whatever the other mass is. So we can just solve for it. We can set it up to be X. X in this case has to be 218. Similarly, we want to balance charge. We started with 86 plus 86. We have 2 on the product side, so everything else has to be in the daughter. We can figure out that that is 84. So we know from that that this daughter nucleus is going to have 84 for the atomic number and 218 for the mass, right? So for the overall mass. So now if we want to figure out what that actual daughter is, we can turn to the periodic table. We can look up 84 is PO, that's polonium. And so we can look it up and we can figure out that our daughter is going to be, we could write our symbol like this, or we could write it out explicitly as polonium 218 or PO 218. Again, you want to interpret, you don't need to memorize that PO is polonium, but that is going to be polonium 218 will always be formed when radon 222 undergoes alpha emission. So when radon 222 decays, you're always going to make polonium 218. All right, so beta decay is then when an electron is emitted from the nucleus. Again, when people first understood that there was particles involved, they gave this the name beta particle because it was the second one they found. They didn't know what it was. We now know that it's just an electron. Okay? So when a particle undergoes beta emission, when a nucleus undergoes beta emission, you just emit an electron. So you'll see it oftentimes written like this, where you have the 0 mass because electrons don't have mass, but then that -1 corresponds to charge, right? Normally on the bottom, we think of it as being atomic number, but it's really just the number of positive protons. We can put a -1 to describe the fact that our electron is negatively charged. I'm going to more frequently use this notation where I put an E in to explicitly call it an electron, but a lot of times you'll see that beta symbol used. So beta decay occurs in nuclei with too many neutrons. So we have an example, phosphorus 32. So it's got 15 protons, making it phosphorus, 13 total nucleons. If that's going to undergo beta emission, that nucleus is going to emit an electron, and what's left over is then sulfur 32. So you can see that what happens in beta decay, because you emit an electron that doesn't have any mass, the overall mass stays the same. So it's 32 nucleons in both the parent and the daughter. Beta decay only emits that you're changing the total charge, not the overall mass, not how many particles are in the nucleus, just what they are. Because the actual process that happens in the nucleus is that a neutron that's in the nucleus becomes a proton and then an electron spits out. So you have a neutron that's just sitting in the nucleus, it changes, becomes a proton, and an electron gets fired out. This potentially means, this hopefully seems pretty bizarre, that you have a particle just turning into 2 different particles. So there's some explanation as to what's going on here. These protons and neutrons that we've talked about have a complex structure where they're composed of these things called quarks. And so there are basically particles in there. And so what happens is they have basically a recipe for which types of quarks are in neutrons and protons. And neutrons and protons, we know, for example, that they have very similar properties, right? Everything about them is basically the same. Their mass, their physical size, all of that. The only thing that's different is their charge. And so you basically just need to flip a little bit of a switch. It interacts via something that's called a weak force. This is the 4th force of physics. You have charge, gravity, strong force that we've talked about, and then the weak force. And so you're changing those quarks, and then you have this beta emission. There's some complicated stuff, but most importantly, the neutron, wherever it was in the nucleus, is now just a proton. And importantly, this electron left the nucleus. And so, when we think about this process, it's functionally, if we kind of can zoom in on it happening, it looks very similar to what alpha decays. You started with, say, thorium, 234 here. It emits an electron, gets spit out from the nucleus, call that a beta particle, or you can just call it an electron. And then you have a daughter nucleus that's left over. And you have a change in the daughter nucleus, that it now has the same total particles, just something that was called proton or neutron is now called proton, okay? Because it has that changed particles, it has that changed character, where you have those different properties. And I'm not going to pretend to understand too much about weak force or changing quarks. It's just this is bizarre. It seems bizarre. This particle just changes, and it is very bizarre. But it is consistent that this is happening where neutrons become protons and spit out an electron along the way. What we're mostly interested in is being able to predict those decays. So for what nuclide is nitrogen-14 the product of beta decay? So this is a little bit different than the last example we looked at, because in the last one, we started with the parent, we wanted to predict the daughter. But here, we're given the product, right? We're said nitrogen-14 is what comes out, so what did you start with? Okay, what was the unstable nucleus that decayed into nitrogen-14? So, we know that we're asking for the product nucleus, so that's going to be that nitrogen-14. Then we want to think about what are the weight and mass of the particle being emitted. We're told it's beta decay. That means it's an electron. And then we go through the same process of balancing, right? We balance the mass, we balance the charge, and then we get that to be lined up. So nitrogen-14 is the daughter nuclide. That's the product that we're creating here. And it's forming from beta emission. So the other product is going to be an electron. And so if we want to figure out where did we start from, what is on the reactant side of our equation, we need to balance our mass. So the electron doesn't have any mass. We're not losing anything. So 0 and 14, we had an initial mass was also going to be 14. For charge now, we have an electron and then the 7 protons in the nitrogen. So those are going to combine. If we add those together, you can see we started still with 6 charge. It was just all in protons. So that gives us the information, the mass and the number of protons in our parent. We can interpret that. That is going to be carbon-14. So we always know that carbon-14 is going to be the parent that via beta decay produces nitrogen-14. So we can use balancing to go back and forth always between parent and daughter. We know that those two are always going to be related via the balancing of the charge and the mass. Participation 1121, question 2. What is the daughter nuclide when potassium-40 undergoes beta emission? This is the second question on participation 1121, due Friday, November 21st at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what is the daughter nuclide when potassium-40 undergoes beta emission? All right, so the third type of decay I want to talk about is gamma decay. And so gamma decay involves the emission of gamma radiation from the nucleus. And so our gamma particle has the symbol of gamma. That symbol is gamma, that is a lowercase, that's Greek. The Greek alphabet is alpha, beta, gamma, so this would be like C. This was the nucleus. This was the third type of radiation that humans figured out. And you'll note there are 2 zeros, 0 mass, 0 charge. That is because gamma radiation, it's called a particle, but it's really just pure energy. It's a photon. It is electromagnetic radiation, so it's a wavelength, it has all that kind of stuff. And so it is just pure energy that comes out of the nucleus. And so what happens in here is this corresponds to what we call metastable nuclei. So you can imagine if you look here on this equation, we have this TC is technetium. And so 43 is the atomic number, and then there's 99M. And so this 99M just becomes 99, and then you have this gamma radiation coming out. And so what's happening here is basically you have a technetium 99 nucleus that's just the orientation of protons and neutrons isn't the most stable. So it kind of like rearranges, kind of like thinking like a Rubik's Cube, kind of like shuffles all the parts. gets to a more stable orientation, and then that releases some energy. But gamma decay does not correspond to a change in the chemical nature of the nucleus. You don't change the number of protons and you don't change the number of neutrons. The mass and charge stay exactly the same. So this is an energetic change of nuclei. It doesn't change the name of the nucleus. It doesn't change the number, anything like that. So we are not going to be as interested in gamma decay. Gamma decay is associated with all nuclear processes, right? Because you can imagine what happens is if you have, say, like your thorium that was doing the beta emission. So this was the thorium does this beta emission, you spit out this electron, and now what has happened is one particular neutron is now called proton, right? You have one new neutron, one thing that was a neutron is now just a proton. And that's going to not necessarily result in a nucleus that has the most stable arrangement of all the protons and neutrons. So, what kind of happens is they kind of rearrange, shuffle around, emit energy out of it, and then you have the exact same, in this case, PA nucleus. I don't know what that is. So you have this PA nucleus that has the same number as it did of protons and neutrons as before, but it's just kind of rearranged. Since we are chemists, we only care about this overall change, right? Gamma decay, we can think about this as like it's an intermediate step. Remember when we talked about mechanisms, right? But we don't really care about that intermediate step where you're emitting radiation or the nucleus is rearranging. I just care, you started with TH34, now you have PA34. I don't necessarily need to know exactly how much energy has come out of that. If you're a physicist or you're using that energy, you probably care. But as long as we're chemists, we can just ignore it. Second participation question in this set of videos. I think that's over halfway. Yeah, we're over halfway through this set. Got a couple more videos. See you there.